Hi, in this chapter, we are going to study bipedal inverted pendulum walking model. After having some introductory session for how we can solve the dynamics using the simplest rimless wheel model, about how can solve the repeated solutions and how can we check their stability. Now we are going to work on bipedal model. So how this bipedal model compared to the rimless wheel, which is not really a bipedal because the there's no swing leg motion. It's been fixed as angle between the stance leg and swing leg with the 2 alpha, and the spokes are automatically coming through forward as it rotates, right? Compared to that, bipedal model has a different dynamics for the stance leg, depicted as a blue line, and the swing leg is a green line independently. So that's how we are going to work on in this chapter, so that we are going to work on the equations of motion and the step-to-step transitions and numerical simulations and so on. So what do you think would be the most unique difference between the rimless wheel versus the bipedal? Of course, the bipedal has a two legs. So compared to the previous rimless model solution step that we are going to briefly take a review, you have equations of motion, and you're going to integrate it over to the collision part. The spoke is coming down to the ground. And at the collision, you are going to apply the inverse momentum relationship to figure that out what's going to be the after collision theta and the angular velocity. It'll going to be reduced by the factor of eta, which is less than 1. And then you just repeat these procedures until you find the steady walking. Of course, for the rimless wheel, you can analytically find out what's going to be the steady state, the initial condition that will result in steady state using the analytical formulation, so you can find the fixed point, but generally you should find it through the repeated iteration, and then we learn how we can check the stability using Jacobian's eigenvalue. For bipedal walkings, as I said before, you have a two legs, so you have a state variable describing the stance leg and the swing leg. So let's say this is a theta and the phi, and then you're going to have and then also we have to think about, is the only a single mass at the center of mass would be enough. Since you want to make a motion for the swing leg back and forth, you need a dynamic equation for that, which means you have additional inertia to describe the swing leg, so that we are going to add a swing foot mass small m. In addition to the capital M is describing where the pelvic, located at the pelvic point, to represent the whole body center of mass. So the two equations of motion for each, like a swing leg and the stance leg mass, or the swing leg motion theta and the stance leg motion theta and the swing leg motion phi will be worked on. And of course, it's gonna be a form of like a similar form of a robot equation, like an inertia term, actuation term, and the gravity term, and the velocity term, and the coupling term between the swing leg and the stance leg. And once we obtain the equations of motion, we are going to integrate up to the collision part, and we are going to also derive how those after collision parameters will be determined from the before collision parameters, etc. So first, let's work on obtaining the equations of motion for bipedal model. Since we have two masses, capital M and the small m, the very first step is define the reference coordinate frame. So first reference coordinate frame will be similar to what we have worked on the rimless wheel. So I'm going to set the coordinate frame for the stance leg here at the contact point, ground contact point, which is parallel to the slope. So capital X and Y, which is inertia frame. And then theta as a counterclockwise. How about the reference frame to describe the swing leg? To describe the swing leg, I'd like to set the reference frame at the pelvic point, P, and then describe the relative motion of the swing leg with respect to that point. Okay, so those frames are not rotating and then perpendicular, similar to the reference frame for the stance leg. I'm going to make it as a perpendicular, parallel to the slope, so x and y. And then since I'd like to define the coordinate with respect to at the counterclockwise, I had a direction as x and y this way. So with that, I have a description for the kinematics for the capital M, capital X and Y as a minus L sine theta and L cosine theta, and its derivative for the velocity and acceleration. And for the small mass, the swing foot mass, I can define the small x and y, the relative position of the swing leg with respect to the pelvis, which is L sine psi and minus L cosine psi. Psi is the angle with respect to the slope perpendicular vertical, and also the phi is a joint angle between the two legs. So joint angle is pretty often used for describing the biomechanics. So those theta, phi, psi are all related. So either I will use the phi and psi and the phi interchangeably back and forth, and then use those terms. So here at this point, I'm going to define the small x and y in terms of psi. Now, there's many other options possible to set the coordinate to describe the swing leg. One other way will be a body attached coordinate frame, which is often used for the multi-segmental biomechanics study. So in this way, your small x and y coordinate, instead of fixed at the space, is now rotating with the body, with the stance leg. So in that case, note that when you are taking the kinematics relationship from the position to the velocity and velocity to the acceleration, when you take the derivative of the unit vector, note that unit vector are under effect of rotational motion. Okay, so in this slides, we are going to work on with the option 1, but definitely you can do the other option for the coordinate selection. Okay, so let's work on the equations of motion swing leg first. So there is only one contact of the swing leg with the pelvis. So that contact force will exert the force, which is Fx and y, and the gravity. Is that it? Well, your coordinate is attached to the pelvic point, and the pelvic point is what is moving with the acceleration, right? So suppose that this acceleration here is AOP, then what else? You should add on your free body diagram. Yes, the inertia force. So since your reference frame is non-Newtonian frames, so the acceleration multiplied by the mass MAP in the opposite direction, so it's minus MAP direction, AP direction, is applied as inertia force to the mass, swing leg point mass small m. So I will split it as x components MAPX and y components MAPY. So there are 5 force components applied for the swing leg mass small m. And this pictorial relationship between the force and the acceleration is transferred as a mathematical form, which is equations of motion. So there are 5 components of Fx and y, and gravity and acceleration, inertial force x and y. That'll result in x and y acceleration. I'm going to set the moment equation with respect to the p, so I just have to consider the moment by the m of a py, and x components of inertial force MAP, and then gravity. So I have 3 terms, MAP, and there's a cross product of L. I just express it as all the sine, cosine components, and MAPY moment components, and then MG moment components will result in angular momentum change, ML square psi double dot. And as I said before, I can exchange it as psi double dot in terms of theta and phi dot, theta double dot and phi double dot. And when you derive this equation by yourself, just note that there are a relationship between the angle for the vectors of the leg length and the force applied. So note that those are angles, and then you should figure that out, which angle is similar, equivalent to which. Now, if I just rearrange them, I will have a form of AP of X and Y and MG again. And note that how you can find out AOP. AOP is actually the you can obtain from the kinematic relationship for the stance leg. So AP, the stance leg acceleration. So if you go back to the previous slide, there is a kinematic relationship of how capital X double dot and Y double dot is expressed in terms of theta. So if you just plug that in, those terms are gonna be expressed as this way. Okay, and then if you just calculate this algebraic manner, then there are some parameters are canceled and some parameters are simplified. So what you can get finally is this form. So let's examine by term. So this is angular momentum change, I theta double dot kind of term. And this one, mg sine theta term, is what? The moment by the gravity. So if this is a minus sign, so that means you have a stable pendulum, right? Pendulum term. And this is additional like activation external force term, external momentum, which is caused by what? The inertia force, right? And then the acceleration here is what? The angular acceleration multiplied by the L, and this one is centripetal acceleration. So this is the equation, looks like the pendulum equation, typical pendulum equation with external force effect by inertial force of motion of swing leg. Okay, let's move on the equations of motion for the stance leg. Stance leg look kind of easy because it's very, very similar to the what we have worked on for the release wheel, except that there is additional contact at the pelvis with the swing leg. Let's see how it look different. So you have a ground reaction force, and this is a passive walking. There's no torques applied, and the gravity and the contact force by the swing leg, which is f of x and f of y. So there are 5 force components. So you can have Newton's law in x and y direction. And moment equation with respect to the ground contact will have a moment effect contributed by fx and fy and mg. So you have 3 terms. And how you can eliminate fx and fy. Well, f and x and fy are from the swing leg equations of motion. So if you recall the swing leg equations of motion, you can substitute f of x and f of y in terms of all the other term you might be interested in. Okay? So if you plug that in, you will have a of p term and small x double dot, a of py, and small y double dot. And then you can eliminate this in terms of theta and phi from the kinematic relationship, what we have described in the few slides ahead. So AP is going to be expressed by the theta double dot, and small x and y, it's going to be psi double dot, or theta and the phi. So if you plug that in, there are some relationship that you could use when you're deriving these equations of motion by yourself later. So if you plug that in, the final equations of motion obtained is going to be this form. Looks a little bit complicated, but components are pretty intuitive. This is the angular acceleration term, I theta dot term. And this mg sine theta term is going to be what? The typical inverted pendulum actuation torque. And those are the centripetal force and acceleration for the swing leg rotational motion effect. And those are the swing leg's gravity term and the rotational motion of the swing mass in terms of theta double dot. So this is typical inverted pendulum equations of motion type with external force effect by the reaction force at the joints, the swing leg rotational motion. Okay, so if we obtain with that, we have a stance leg equations of motion like this and swing leg equations of motion like that. It looks a little bit complicated, so let's make it a more simplified form. So let's define the ratio beta as a mass ratio between the swing leg mass, small m, in terms of capital M. So we have equations about the beta. And that's, we can have all the acceleration term multiplied by the inertia and velocity term and the gravity term. So it pretty much looks like what? The robot equation, right? And then when you have an active walking, you can actually add torques. So pretty much similar to the robot equation. So equations of motion for the bipedal walking is pretty much similar to typical multi-segment dynamics. Okay, so let's assume we have linear risings for the higher order term. So higher order term can be approximated to be negligible compared to the first order term with the linearization. So those square term can be ignored, eliminated. And assuming that the beta, the mass ratio is going to be very, very small. So your compared to your body mass, your foot mass is really, really small. Then what you can get is you can compare to this one, like a 1 plus very small number is going to be approximate as 1. Same for this one. 1 plus beta is going to be approximate as 1. Okay, what else? Here we have a beta multiplied by the phi double dot. So since the beta is really small, can I just assume this one is 0? Well, you have to be cautious about just ignoring this because you never know what are the order of magnitude of this theta double dot. So when you ignore those small beta term, you should also always compare the relative order of magnitude of the beta contribution in the equation. So if I rearrange this, okay, the second equation can be written in terms of something like a 1 plus beta term multiplied by the theta double dot. So here, now I can say that, okay, so this beta effect compared to this one, it's going to be considered to be small. So in that case, I can just assume approximate this is going to be negligible. Okay, so if you just have to check by the rearrangement if those beta term can be ignored. So final equations of motion I can get, the approximated equations of motion is going to be one for the theta double dot and the other one for the phi double dot. So theta is for the angle for the stance leg, phi is the joint angle of the swing leg with respect to the theta. Now, what it looks like is what? Oh, this is pretty much same for the rimless wheel, right? So you have an inverted pendulum with the force source only by the gravity on the incline. And then maybe you are curious why there aren't any effect about the swing leg, because swing leg mass is very small. So those dynamics doesn't really change the dynamics for the stance leg, which makes sense, okay? And how about the swing leg dynamics? Swing leg dynamics, instead of minus, this one has a plus, phi double dot plus mgl sine phi. So it's pretty much like a pendulum, just pendulum motion, right? And then you have an extra term for the theta term and theta double dot. So this one behave as external force source, like since you have inertial force applied by the stance leg motion, that is applied to the pendulum motion of the swing leg, which does make sense. So stance leg like a inverted pendulum equation, swing leg like a simple just pendulum equation with the additional force term by the motion of the stance leg. So the gamma is the only free parameter here. So this is what you can get for the simplified form. And if I just approximate the behavior, like similar to the rimless wheel, theta is gonna be like a monotonic increase, and for the swing leg, there is gonna be monotonic decrease. So actually, when you actually calculate the solution, you might be working on in maybe next week. This is the solution, typical solution type for theta and phi. Okay, so far we have obtained the equations of motion for the bipedal, simple bipedal inverted pendulum model. You can also obtain the equations of motion use Lagrange equation. So I'm going to just briefly go over the very first step is you have to define the generalized coordinate, and generalized coordinate is usually calculating for the work. So prefer to define in the inertial frame. So from the inertial frame, I will define the angle with respect to the ground parallel, not the slope parallel, because I have to define the gravitational energy, potential energy. So Q1 is defined by this angle, and the Q2 is defined by with respect to the earth vertical. So all those Q1 and Q2s are also related in terms of theta, phi, and psi. And your position is now can be expressed as a generalized coordinate Q1 and Q2. So your kinetic energy is simply just kinetic of this particle at the pelvis, the center capital M, and velocity of the small m. So the capital M kinetic energy is mv squared, and the small mass is m 1/2 m small m v squared. V squared term is this one. And the velocity, you have a gravitational energy for the capital M and the small m, and then if you just plug that into the Lagrange's equation, what you can get is this one. And this looks like pretty much similar to what we just have obtained using the Newton's law. And if you just substitute the Q1 and Q2 in terms of theta, phi, and gamma, what you can have is what you would have is exactly equivalent to what we have just derived using the Newton's law. So I strongly recommend you to work on the Lagrange's equation as well. Okay. To summarize, we have gone through all the steps. We have just started we are going to go through all the steps while we have worked on the rimless wheel in this chapter using the bipedal model. So we just worked on the very first step, obtaining the equations of motion for the bipedal. So this one is a simple rimless wheel equations of motion. Now we had two equations of motion set for the stance leg and the swing leg and some coupling term. Okay, and then we have a simplified form as well. The next step what we are going to work on is take an integral of this up to the collision. So how we could define the collision here for the bipedal. So for the rimless wheel, what really happened is the angle is gonna be like a relationship for the alpha, right? For the triangle with the two lengths together, same. You have a theta equals alpha kind of condition to indicating collision occurring. How about the bipedal? So this is going to be initial posture, and what will happen is your swing leg goes over to the front and then collision occurs here, right? So you're going to have a same angle for the stance leg and swing leg. So for the symmetric leg, so this is going to be a condition for you to stop integrating and working on the collision. But note that for the bipedal, you have another similar posture that will satisfy this condition. So when your center mass moves up in the mid stance, your swing leg moving from back to the front, there are the case where your two angles overlap. So you should do some constraints that you are not going to consider that posture as collision. So this will help. Okay, so for next part, we are going to work on how we can obtain the collision equation for the bipedal. Thank you for listening.